Yes. So thank you, everyone. So as is often the case, I'm here to deliver the bad news. This seems to be my lot in life. I have this role in every differential privacy event that's ever occurred. So unfortunately, there's a lot of bad news. I think I'm giving 5 talks on bad news. And so
One of yours is good news.
one of mine is good news. 5 are bad. I'm a net -4 for this workshop. So there are many, as Katrina said, sort of every time we introduce a differentially private algorithm, the first thing we want to do is prove that it's private. And then the second thing we want to do is prove some kind of corresponding accuracy theorem. And then I show up, and sort of the third thing that I'm going to make you do is hopefully prove that this algorithm is actually optimal. So we want to be able to say for a given problem of interest that a certain differentially private algorithm is actually the best algorithm for solving that problem. So we've seen several algorithms already, randomized response, the Laplace mechanism, the exponential mechanism, the small dB mechanism, and all of these solve sort of different problems with different guarantees, and we want to know, at least when possible, kind of which one is the best. And so we're going to see a couple different techniques. There are kind of 3 main techniques for proving lower bounds on the accuracy of differentially private algorithms, one of which we'll see right after this, and the next we'll see, I think, on Thursday. But the first one, and I think in some sense the simplest one, is called packing lower bounds. So packing lower bounds, which originated in the works of Hart and Talwar and Baimol, Sivaswanathan, and Nissim, it's kind of a very nice technique for proving lower bounds, at least for this kind of strong definition of differential privacy, the sort of pure epsilon 0 version of the definition. So, and in particular for this kind of like pure, unadulterated differential privacy, this is kind of the right technique for proving lower bounds for most problems. So it's a good one to start with. And kind of the take-home messages that I want to get across in this talk, I want to explain sort of what is a packing argument and how you can use it to prove lower bounds for differential privacy. And I'm going to show both a sort of general statement of what this technique is and also some specific examples. And another point that I kind of a secondary point that I kind of want to make is that not only is this a good technique for reasoning about this pure version of differential privacy, but it actually shows that this pure form of differential privacy is much more restrictive and gives lower accuracy than the kind of general approximate form of privacy. And so I think this motivates that in general we should actually look at the sort of most general definition. But we should start by looking at the sort of simplest definition, of course, and get where we can get very precise statements. So, all right, and by the way, so these lower bounds talks tend to be a little more intrinsically technical than some of the the algorithms. So I'm going to try to keep things at sort of as high, clean, simple level as possible. But if anything is getting sort of lost, please stop me, and I can try to give more detail on the board or just answer questions. So generally keep me on my toes to make me answer questions and clarify. So what is the main idea? So let me just explain at kind of a high level how you would try to prove sort of a lower bound for differential privacy. And it is the following. So suppose you have some problem you want to solve, and it takes a data set in this cloud. So this is sort of all data sets of size n, let's say. And it produces some output. So maybe this is a real number if you're trying to compute the answer to a counting query. Or it could be a small database, any output range. And now your function is just a mapping from a data set like this one to some output in the output range. All right, and what a packing argument does is it tries to find sort of many data sets in the input space that are close together, where close together is going to be sort of in the sense of differential privacy. So close together in the sense that they differ on kind of a small amount of the data set. but under this function you're interested in computing lead to like very different outputs. So that's the sense of packing. It's just the usual geometric sense. You're trying to pack different outputs that are far apart. You're trying to get many outputs that are far apart. And now, just intuitively, if we had a differentially private algorithm that takes a database and solves this problem, it sort of computes f of x, then you would get some kind of contradiction. Of course, the actual contradiction is going to happen in the like quantitative bounds, but just intuitively, your algorithm M is supposed to take any one of these databases, like x1, and produce an output, f of x1. Sorry, I'm favoring this side of the room with my pointing. So right, your algorithm, if you've designed it well, is going to take one of these databases, like x1, and it's going to produce an output like f of x1. And what that means is that if the algorithm is sort of accurate, if it solves your problem, then there must be kind of two data sets that are close in the input space, but for which the algorithm produces very different outputs. Right? That's sort of what it would mean to be accurate, is that if I run the algorithm on x1, it maps to f of x1. If I run it on x2, it maps to f of x2. And those are far apart. On the other hand, since I've chosen these data sets to be close together, differential privacy is going to imply that the distributions mx1 and mx2 are close in some sense. Okay, and obviously, for the right definitions of close and far, these are going to be contradictions. Now, one thing that makes the picture a little more complex is that, as we've seen, I think, in fact, as you proved, like non-trivial differentially private algorithms have to be randomized, and they have to have some notion of approximation. And so the algorithm doesn't really map x1 to f of x1 or x2 to f of x2, but instead there's some set of kind of good outputs for each data set. So these might be all the outputs that are within some alpha of the correct answer. And because we've made the outputs far apart, because we have a packing where all the outputs are far apart, these sort of clouds of good answers around each output are going to be disjoint. Okay, so that's just sort of a very intuitive sketch of what a packing argument is trying to do. And now, we're going to prove sort of a general packing lemma that's going to let you kind of come up with a recipe for proving lower bounds for sort of any problem in differential privacy. But let's first work through a very simple example, and we can also review some of the algorithms we saw as we go. But the first thing I want to do is I want to remember one property of differential privacy that's going to be kind of the only kind of crucial mathematical statement that we're going to use in the whole talk. And it's this thing that I think Katrina called group privacy, and was on the review problems last night. So remember, differential privacy is defined in terms of these neighboring data sets. So you have two data sets, x and x prime. Each of them has n records or rows, and they're neighbors if they differ on at most one row. Okay, and then there's some subtlety, like are you adding a row, removing a row, swapping a row, but it's not important for this. Okay, and we can generalize this definition. We can say two sets are m neighbors, or have distance m, if they differ on m rows. All right, and differential privacy, even though it's defined in terms of neighbors, it gives some statement about privacy for m neighbors. So it says that if you have an algorithm that's differentially private, it's epsilon 0 differentially private, then for every set of m neighbors and every event s, the probability of S under data set X and the probability of S under data set X prime differs by this ratio of e to the epsilon m. So privacy kind of just degrades linearly with m, the distance between the data sets. So this is a property we're going to use sort of in one crucial place, but it's kind of the thing that makes everything go through. And just a small note, I keep saying that this is sort of the right argument for epsilon 0 privacy, but somehow is not the right argument for epsilon delta. The reason for that is because for epsilon delta, we don't get such a nice statement of group privacy. So as you saw in the review problems last night, if you stuck around for those, you do get some group privacy, but it has sort of a weaker Like it degrades sort of faster in M, and that's sort of exactly the difference between why this argument gives tight lower bounds for epsilon 0 and tends to give like garbage when there's a non-zero delta. Okay, good. So that's all the preamble. So let's actually see a packing argument in action. So I'm going to show like a tight lower bound for computing the histogram of a data set. So like a very, very simple to define problem. I think Katrina talked about it sort of explicitly. So, I'm just going to think of the data set as sort of counts of each type of records. Like my data set has n rows. They each come from some universe big X. And I'm just going to think of the histogram of the data set as sort of the number of rows of each type. So like, how many people gave me exactly this data? How many people gave me exactly that data? So it's just a histogram like this. It's like a bunch of counts that sum to n. That's all it is. And now, I want to release some approximation to the histogram. And to keep things simple, I'm just going to ask for like a very weak approximation to the histogram. What I want you to do is I want you to release some new histogram h hat with the guarantee that sort of point-wise h and h hat differ by n over 3. Okay. So every number in the histogram is between 0 and n. So this is like non-trivial accuracy, but pretty weak. But we're proving lower bounds, so that's good. We're getting, we prove a lower bound even for a very weak approximation. Okay, so in pictures, like the blue histogram is your data. I want you to release something like the orange histogram. And I want that, like, for every one of these bars, the heights differ by at most n over 3. The problem makes sense? A pretty, simple elementary problem. And using the language I described, yeah?
Does the fact that you can't have non-negative results affect the privacy here?
What do you mean? So
You can't have negative results. I mean, you're...
No, so like if I had any algorithm, even if it produced negative results or produced results bigger than n, by the post-processing property of differential privacy, I could take everything negative and round it up to 0, and that wouldn't affect privacy and can only make it more accurate. Okay. So in this language that I sort of sketched out earlier, I'm going to say that for every data set x, I'm going to define the set of good histograms for x to be all histograms h hat that differ by at most n over 3. So that's our goal. Our goal is to take a data set x. You can even treat x as a histogram if you want. And I want to output a good histogram for x, which is just any histogram that's sort of point-wise close. Okay, so let's just do some quizzing. So I want some audience participation. So we've seen this Laplace mechanism as a way of answering any numeric valued query. So if I wanted to use the Laplace mechanism to produce a private histogram, how much noise would I have to add to the histogram? How would I do it using Laplacian noise? And I will wait you out. One over epsilon. And that's on each entry? Good. Okay, that's right. So even though there are many, many different buckets of this histogram, changing one row of the data set can only change one of those buckets. So I only need to add noise proportional to 1 over epsilon to each entry. And if you want to talk about swapping rows versus adding rows of the data set, it might be 2 over epsilon. Okay. So now we know an algorithm, we have an algorithm in mind. We have a private algorithm, which is add noise 1 over epsilon from a Laplace distribution to each bucket. So of course, we need an accuracy theorem. So what does this algorithm give? And the way I want to think about what this algorithm gives is how big does n have to be before this algorithm is meaningful? I'm adding noise 1 over epsilon. The noise is sort of fixed independent of n. The bigger I take n, the more accurate the result is going to look. How big does n have to be in order to get this notion of accuracy? This one's a little trickier, but feel free to just throw out answers. Don't make me point with the laser pointer. So I want the two histograms, right? I want to take H, and I now add noise from a Laplace distribution to every entry of H to get some new H hat. And I want that every entry of H hat is close to the corresponding entry of H. So like, what's the largest noise that I add to any bucket? Sorry, speak up. Well, I want it to be n divided by 3, but like this is my algorithm. It adds noise 1 over epsilon to each bucket from a Laplace distribution. So how big is the noise on the largest bucket? It's like at least 1 over epsilon, right? All right, so inflated me out. So if I add noise from this distribution, and I add noise to size of the domain many buckets, the largest entry will have noise about ln x over epsilon. So Katrina mentioned this property of the Laplace distribution that if it has parameter b, then the probability that it makes a deviation of size t times b is sort of exponentially decreasing in t. So if you just take a union bound over all of the buckets, you can show that every entry has error at most ln x over epsilon. And this is actually tight, so it's both necessary and sufficient. And so what this means is that to get this definition of accuracy that I defined, I need n, the size of the data set, to be bigger than ln of the universe, so ln size of x, over epsilon. Okay, so that's like a good-looking accuracy statement. We say, if my data set is big enough, then this is the error I will get. And what I'm going to prove is that this is essentially tight. So I'm going to prove that under this pure differential privacy notion, this epsilon 0 notion of privacy, then if I have any algorithm, so Laplace noise, Gaussian, like any noise you can come up with, if I have any algorithm, and the probability that it gives me an accurate histogram, so the probability that it outputs a good histogram for x, is at least some kind of arbitrary constant 1 over e, it's not really important, then it must be the case that my data set has ln x over epsilon records minus 1. It's like the tightest lower bound I'll ever prove. It's tight to within 1. Okay, so animation fail. So we're going to do this using a packing argument. So we need to define a lot of data sets that are close together, right? Like that's like the first step of the packing argument is define a bunch of data sets that are close together. And so here's my packing of data sets. And I'll just view them as histograms, sort of, if you wanted to make them data sets, it's not hard. I'm just going to, for each entry, like for each possible record in the data set, I'm going to define a data set that's just entirely, like just n copies of that row. Okay, so these are just sort of like, take some record, repeat it n times, that's your data set. So that gives me size of x many possible data sets. And the key property, as I said, right, we want that the outputs, the correct answers for these data sets are far apart. And notice, like for these, they're sort of as far apart as they can be. Right? In particular, there's no histogram I can output. Like there's no way to come up with a histogram that's accurate for 2 of these data sets at the same time. And why is that? Because if I'm accurate for, say, P1, then I have at least 2/3 records of type 1, but that means I have at most 1/3 records of type 2, so I can't actually be accurate for P2. Okay, so these sort of match my picture that I have many data sets, and their outputs are far apart. And they're so far apart that if I draw a little cloud of good outputs around each point, those clouds are completely disjoint. Okay? So let's see how we can use this to actually prove the lower bound. Oh no, I didn't animate these. We'll see how we use all the properties. So here's how the proof works. So let's start with a fairly simple statement. So because all of these sets are disjoint, right? Because for every element of my packing, the good set is disjoint. If I sum over the elements of the packing of the probability that when my alleged algorithm is given the first element of the packing, or any element of the packing, some arbitrary element of the packing, if I sum this probability over all elements of the packing, it must be at most 1, because I'm just summing up events that are disjoint. Okay? Pretty simple. So here's where I've used the property that the good sets are disjoint. So check, we've used one property we need to use. Now, I told you that the only property of privacy we're going to use is this group privacy. And in order to use group privacy, we want all our data sets to be close. So here I'm abusing the notion of close. Like how far apart are these data sets that I've defined? As far as possible, but what's an upper bound on how far apart they are? 2n. I'm going to say n because I like the definition where you swap rows instead of add and subtract, but up to this factor of 2, it doesn't really matter. So yeah, they're n apart. So that's, it's a weak upper bound, but it's an upper bound. And so what that means is that, oh no, I botched this. So if I swap in p sub z here instead of p sub 1, let me write it on the board. Board is very shaky. Okay, so by group privacy, if I swap in, instead of the data set P1, the data set P sub z, then I have to pay this multiplicative factor of e to the minus epsilon n. That's a big factor, right? We're changing the probability a lot, but at least we're not changing it by an unbounded amount. The probability can't go from 0 to something non-zero. All right, so now by accuracy, since we've conjectured that our mechanism is accurate, we know that the probability that when I give it p sub z and put it into and have it mapped to the good set is at least 1 over e. That's our assumption, is that there's some probability that when I give you a specific element of the packing, you end up in the good set for that element with probability 1 over e. All right, but now, the packing is big. We're summing over a huge number of data sets here. So in fact, this quantity is exactly equal to the number of data sets in the packing, size of x, times e to the minus epsilon n minus 1. That's where this annoying minus 1 comes from. All right. But notice we have 1 upper bounds some quantity that is decreasing in n. So as n gets big, we can satisfy this equation. But if n is too small, we can't. If n is 1, there's no way we're going to satisfy this equation. And specifically, if you just rearrange, we get that in order for these inequalities to be satisfied, n has to be at least log of the domain size, minus 1, over epsilon. Okay. Does the argument make sense? So this is the mechanics of packing. So you come up with many data sets that are close, at least a little bit close to one another. You use the fact that they're disjoint to say that there are many different good outputs. And if I fix a data set, the probability that it lands in each of those good sets sums to at most 1. Then we use privacy to swap in the correct data set for that output. And then we do some algebra and get a contradiction. So let's see like generally like what happened. Like let's see sort of an abstraction of this technique. So this is going to give you some way of getting a lower bound for like any problem through this sort of recipe. So you define some problem. You have some function f you want to compute. You want to find a good data set, like a good synthetic data set. You want to pick a winner in an election. You pick any problem of interest. And for that problem, you're going to have some notion of accuracy. So like you've done like Katrina's step 2, you've proved an accuracy theorem. And now you have some notion of accuracy that gives you this family of sets G of X. So for every data set, for every database X, there's like some subset of all possible outputs that you would be happy getting for that. You would consider that a good answer for your data set X. So now with respect to these sets of good outputs, an M packing is like a big collection of data sets, hopefully a big collection of data sets, such that for every pair of data sets in your packing, they're close, they're within M. So in our previous example, M was N, but M could be anything. And yet, even though these data sets are somewhat close, the good sets for all these data sets are disjoint. Okay, so that's exactly like the picture I drew in the beginning. This is just sort of a formalization of the concept. And we have this sort of general packing lemma, which is really like falls right out of the proof we did before, that says if your set P is an M packing, it's a bunch of data sets at distance M, and allegedly we have some algorithm that takes a data set and produces a good output for any data set with probability 1 over E. Again, 1 over E is sort of arbitrary. Then we get a lower bound on M. Okay, we get a lower bound on M, which is the distance of the packing. And the lower bound says that M has to be at least log P over epsilon, up to this -1 in the numerator. Okay, so in our example for histograms, we had an N packing. We had data sets that are N apart. And we had size of X, many of them. So we got a lower bound that said N has to be bigger than ln of the universe size, ln of size of X over epsilon. Okay, but we can do this like generically for like sort of any problem of interest. So first, let's just go over the proof one more time. It's basically the exact same thing we did, but let's just go over it once more to like drive it home. So first, we use the fact that these sets are disjoint to say that if we single out like any element of the packing, and we ask what is the probability that M outputs something that's good, not for that element, but for some arbitrary element X sub Z in the packing, and we sum over all the Z's, then this is at most 1. Now, applying group privacy, using the fact that every pair of data sets in this packing has distance M, we get that if instead we sum not the probability that M of X0 outputs something in GZ, but the probability that M of XZ outputs something in GZ, those probabilities differ by at most e to the minus epsilon M. Okay, and now by our assumption that this algorithm is accurate, this probability is at least 1 over E. And the size of the packing is, by definition, size of packing. And rearranging, we get the lower bound I promised. Okay, so this is cool. We have a way of proving a lower bound on the accuracy of like any algorithm that satisfies epsilon 0 differential privacy in terms of this kind of packing property. And this is nice because packing is like sort of an intuitive, it's a fairly intuitive like geometric property. Like for many problems, both they're sort of like intuitive ways of coming up with these packings. Like it's not some completely like intangible type of thing. And also in some cases there are actually like sort of geometric power tools that you can bring to bear on the problem that guarantee the existence of these packings. So it's a very like nice framework. It sort of ties into things that are well understood, which is cool. Let me pause for a second in case anyone has sort of questions about what we've done so far, about the sort of general packing approach to proving lower bounds.
It can be viewed both as a lower bound on the amount of data you need and the size of epsilon, right? Depends how you look at it.
That is true, yeah. So you can rearrange these things. So yeah, so often you can rearrange these things. You can also, in the first problem I introduced, there wasn't really like an accuracy parameter, but you can of course also view it as a lower bound on some like notion of accuracy. So we'll see an example where you can treat it either way. Okay, so let's see another example. So let's see one more kind of concrete example. And this is going to be a nice example because it's going to be sort of our first lower bound for this kind of query release problem that Katrina talked about when she introduced the small DB mechanism of answering many counting queries. But I'm going to phrase it as like an even simpler problem. So I'm going to phrase it as the following problem. You have a data set where the universe is like d-bit strings. Or in more like kind of operational terms, you have a data set where every person in your data set answered D, like yes or no questions. Okay, they just gave you like a binary vector of length D. And all you want to do is you want to compute the mean of this data set. You want to know the average of the rows. Okay, or equivalently, like for each of these D binary questions, you want to know like what fraction of people gave you a yes answer to that question. All right, and you want to do it with alpha accuracy. So like, there's some like math on the board. The notion of a good answer is just that I give you a vector of D numbers such that, for every entry of the vector, it's within alpha of the corresponding entry of the mean. All right? So that's the problem we want to solve. Like I've come up with a problem. I have a definition of accuracy. Now let's, go back to like quiz mode. If you want to solve this problem with the Laplace mechanism, how much noise do you have to add? Like you're going to use Laplace noise for each of the D entries of the mean. What magnitude do you have to add? You look like you're thinking. D over epsilon. Almost. D over n epsilon. Right? So each entry of this is an average of n bits. Right? So the mean, let me draw it out. Nope. All right, so my data set looks kind of like this. So each entry is an average. So if I change one row of the database, I can change each entry by 1 over n. And what that means is that if I have this whole vector of length d and I change one row of the data set, I can change each entry, I can change the vector in L1 distance by d over n. This is the L1 sensitivity that Katrina talked about. So that's going to be our algorithm. We're going to add noise from a Laplace distribution, magnitude d over epsilon n to every entry. And now I'm not going to torment you about log factors and union bounds. I'm just going to say that this is alpha accurate, where alpha is about d over epsilon n. There's an extra log factor in here from some union bound. It can be removed if you work a little harder. It's not really the point. Let's just say alpha is d over epsilon n. Let's just keep things simple. Okay, so we can solve this problem with alpha accuracy, where alpha is d over epsilon n. So, there's a ready-made example. Why did I go on the board? So, let's prove that this is tight. I want to prove that this d over epsilon n is the best accuracy you can achieve for this problem. Yeah? Well, so I'm adding Laplace noise d over epsilon n to every entry. Does it make sense why that's sufficient amount of noise to add? Right. And so now when the accuracy I'm asking for is what is the largest error on any entry of the data set? Yeah, so the ln comes from another union bound, but in this case, because we're already paying a factor of d, like, No. So I like to prove tight bounds, so I lie sometimes. So let's prove that this is tight. So we need to come up with a packing, right? So what we need to do for the packing is we need to come up with many data sets such that no answer, like no vector that is the purported mean, can be an accurate mean for more than one of these data sets. And so the way I'm going to do it is as follows. I'm going to take an arbitrary d-bit vector, call it z, so some row of the data set, and I'm going to copy it not n times, but I'm going to copy it 3 alpha n times. So I'm going to have data sets that look like this. There's going to have some fixed row in the first, several entries, and then just zeros everywhere else. Okay? So I picked a vector z. Now I copied that vector about alpha n times, and then I pad the rest of the data set with zeros. So those are the elements of my packing. And the nice thing about this is that the way I've constructed the data set, for any element of the packing p sub z, the mean is just 3 alpha times this vector z. Okay, so the mean of this data set is just like this vector z that I put on the top multiplied by 3 alpha z. Okay, and now, what is a good answer for one of these data sets? Well, it's going to be some vector where for every single entry, it's within alpha of the true mean. Okay, and so what that means is that if z has a 1, then the corresponding entry of my vector is going to be at least 2 alpha. And if z has a 0 in some entry, then the corresponding coordinate of the mean is going to be at most alpha. So I can distinguish, what is the value in each bit of z. And what that, of course, means is that you can't be accurate for 2 z's. Like every pair of z's differ on some bit. Giving you any accurate answer lets you uniquely recover z. So you can't have anything that's accurate for 2 z's. All right, so we have a packing. Its size is easy to see, is just 2 to the d. And its distance is 3 alpha n. So this is the m. So every data set in my packing differs from every other data set in my packing on 3 alpha n rows. So that's my m. So my packing lower bound is going to say that m, this parameter, has to be at least log of the size of the packing, minus 1, all over epsilon. And m is 3 alpha n. So I get the following lower bound. And as Yehuda pointed out, I can rearrange this to get a lower bound on n for a given alpha, and epsilon, and d, or I can rearrange this to get a lower bound on alpha for a given d and an epsilon. It doesn't really matter which you do, but I presented the accuracy theorem as saying I can achieve alpha equals d over epsilon n. So I'm going to just rearrange this to say that, where'd it go? To say that alpha is at least omega d over epsilon n. Okay, so this is a tight bound up to constants. If you work a little harder, you can probably get a better one. Okay. Yeah?
Just repeat how 3 alpha n first came up.
So the reason I chose 3 alpha n is because I want to say that if I get any vector that's within alpha of the true mean, like point y, like for every coordinate within alpha of the true mean, then I want to claim that that vector cannot be accurate for 2 different elements of the packing, right? It would work with any quantity strictly bigger than 2, if that helps at all. Okay, so now, what is going on? Okay, so now let's relate this to the query release problem which is this sort of like all-important problem that comes up everywhere that Katrina introduced. So if you remember, we have this class of queries called statistical queries. I like to call them statistical queries. Katrina called them linear queries. That's like sometimes informative, sometimes weird. But it's the same thing she defined. So I have queries of this form, where the query has some function that maps rows of your data set to 0, 1. And you just want to know the average of that function over the n rows of the data set. Okay? That's a very general but like nice and elegant family of queries. And notice that the mean is just some set of d statistical queries on a data set whose entries are in 0, 1 to the d. Right? Like it's just the queries of the form, tell me whether the jth coordinate is 1 or 0. So the theorem that I asked you guys to recall for me about Laplace noise says that we can take any k statistical queries, like not just these, like any k statistical queries, and we can answer them up to error about k over epsilon n. Put this log factor thrown in. And we just proved a theorem that says even for the special case of the mean, so like even for a specific algorithm, which is just, so a specific set of queries, which is just the mean, no algorithm can achieve alpha better than k over epsilon n. Right? And the only thing we really used is that you need to be able, there need to be few enough queries that you can include the mean. Right? So if k is much bigger than d, I can't get a k-dimensional mean. Like I can only get a d-dimensional mean. But at least when the number of queries is fairly small relative to the size of the universe, size of the domain, like relative to the dimension of the data, there's no way to get better accuracy than the number of queries over epsilon n. Okay, so you have to get this linear dependence on the number of queries in the accuracy parameter. But now, you just heard a really cool talk from Katrina, where she said that using this very cool small dB algorithm, you can get a logarithmic dependence on the number of queries. So what am I talking about? What sort of lies am I peddling here? Or Katrina, I don't know. Which one of us is lying? Which one of us is a dirty liar? Can someone tell me how to why there's no contradiction? Yeah? So actually, in Katrina's case, they were arbitrary statistical queries. I mean, they were within this definition, they were arbitrary. They're not completely arbitrary functions, but. So did anyone look really closely at the accuracy bound Katrina gave you, or was she just so captivating that you'll just believe anything she tells you? Yeah? No, so it's the same class. I shouldn't have messed with the notation, but it's the same class of queries. Okay, so if you go back to your slides for Katrina's lecture, if you want, or you believe me. So the accuracy theorem she gave had a logarithmic dependence on k, but it actually also had a factor of log of x, log of the number of possible database rows you could have. So this fancy algorithm that gives you this logarithmic dependence on the number of queries kind of only kicks in, it only improves over adding independent noise when the data comes from a bounded a bounded universe. And intuitively, that's because it's correlating the noise on the different queries. But if you look at something like the mean, there's no correlation between the queries. They all touch independent parts of the data. So this you can see as a proof that says we really can't do better than Laplace unless there's some relationship between the queries. So there's some range where we can't do better, but like shockingly, somehow that's like all we need. Like once you have any relationship between the queries, you can get this like logarithmic dependence, and you can do like amazing things. Okay, but this is a good thing to keep in mind. So when you have kind of data with a big domain, like a really, really big domain, like bigger than exponential in the number of queries you're asking, then you actually can't do better than just the simple Laplace algorithm, at least for epsilon 0 privacy. Then another point that comes out of this lower bound for the mean is that you can see that actually this delta, this like little silly like approximate definition of privacy that seems kind of like an afterthought is actually really crucial. Like it really affects the answers we get for privacy. So using fancier techniques, which I think like Kobe is going to talk about later, using sort of a more clever composition theorem for differential privacy, you can actually show that if you allow a small delta, like a negligible delta, just not 0, then you can actually answer k queries with error that grows more like square root of k. This is like a very like, beautiful property of privacy. You can get this error that grows as the square root of k, not as linear in k. And we just proved that that cannot be done under epsilon 0 privacy. So we've actually already seen like a polynomial factor gap that says if you want to achieve this pure notion of privacy, you actually need, like in this case, quadratically more sort of data or more error. So I think that's it's a cool thing to keep in mind. Like this epsilon 0 notion is very appealing and very clean, but it's actually like sort of weak in some sense. Like it seemingly like gives too strong a privacy definition because it doesn't let us do all the things you can do with epsilon delta, which is actually like a sort of morally equivalent notion of privacy. On the other hand, it's like this also demonstrates why this packing lower bound sort of can't be useful for epsilon delta privacy, because it like would sort of prove things that we now know are false. So we'll see later like very different techniques that are useful for reasoning about epsilon delta privacy. So I had one more example, which I didn't really think there was any chance I would get to. And not surprisingly, I didn't. But if you look at it in the slides, you can see it. So I just want to make one like quick point. So like, I don't know, maybe not in a crypto audience, but like in an algorithms audience, like if someone says packing, the audience like immediately yells covering. It's like a call and response kind of thing. So there's this like, these two problems are sort of these dual geometric problems. In a packing, I'm trying to find like many clouds of outputs that are disjoint. In a covering, I'm kind of trying to do the opposite. I'm trying to find a small number of outputs such that, for every one of these clouds, it intersects with the covering. Right? So like if I have these 5 little clouds, there's kind of like 2 points such that one of those points is in every one of the clouds. And it turns out, I'm just going to state this without any evidence, that using the exponential mechanism that Katrina just taught you, if there is a covering of the set of outputs, then you can use the exponential mechanism to select one, and your error will be kind of logarithmic in the size of the covering. And it turns out that coverings and packings are like very tightly related. Like that's why like in an algorithms audience, you say one, people just yell the other for no reason. So what you can basically say is that there's actually a somewhat tight relationship. So not a completely tight relationship, but in some sense packings, like the size of a packing, sort of governs the accuracy you can achieve under differential privacy. So you don't get completely, like you can't prove sort of completely tight bounds this way, but it gives some evidence that this is really like the correct way to prove lower bounds for epsilon 0 differential privacy. So pretty much like, when you go out and you become like differential privacy researchers, like this is a good thing to keep in mind. Like anytime you want a lower bound for epsilon 0 privacy, anytime you want to get a sense of whether you have the best possible algorithm, this is really like the right approach to do it. So I'll leave you on that thought, and then we can take a break.